Pretty sick.
Okay, so good afternoon. Do you remember we started talking about the applications of integrals, but we learned about areas a little bit. Today we want to continue and learn about how to use integrals to calculate volumes, to determine volumes. And there are three methods that you need to know. So the first method, as you see here, is called volumes by slicing. I have written you the summaries here: volumes by slicing, solids of revolution, and method of cylindrical shapes. And I have written you a little bit brief summary of when these methods will be useful in particular. So which method you choose, that is up to you, but sometimes one of them is more suitable for our purpose and for the solid that we are actually considering. Okay, so the first thing that we need to know is this method of slicing. Well, we have to generalize a little bit, because usually when I talk about a cylinder, what comes to your mind is just something like a pipe. That's a cylinder, okay? But in mathematics, even a rectangle is also a cylinder. Okay, so when we say a cylinder in mathematics, it means that we have two plane regions that are congruent, they are identical from any aspect, and then we have two they are on parallel planes. So if I have two parallel planes, it's very hard to draw them by hand, but I want to give you the feeling. So let us say that I have two parallel planes, and then I pick up a closed region here, but I have to be able to draw exactly the same region down there. Okay, so it's a little bit hard, but imagine that's the same thing. They should be exactly identical. Then I start connecting each point of this one to the corresponding point on this line. So then I will probably get an object. This is also called a cylinder. So that is the most general cylinder that we have in mathematics. These two should be completely identical. Okay, so what does it mean? It means that if I intersect my cylinder, okay, by any parallel plane, the cross section will be another identical congruent region. Yes? Is that understandable? So in that perspective, for example, if I take this to be a square, and then I will draw another identical square down there, and I do the same thing here, then what I generate is actually a cube. Or if this is higher than the side of the square, it will be a rectangular cube. So by this definition, rectangular cube is also a particular case of the general cylinder. Is that understandable? Yes? So this is a cylinder, cube is also a cylinder. Why cube is a cylinder? Because the region top there is a square, and the region down there is an identical square, and then I'm connecting corresponding points of the square above to the square below. Then I will make it. Okay, so that is also a cylinder. Okay, and then we have to take this for granted that the volume of a cylinder is the area of this region multiplied by the distance between these two parallel lines, which we call it the height. So the volume of a cylinder is taken to be as an axiom, which is A times H. Okay? And of course, the cylinder that we are usually used to in mathematics, it is called circular right cylinder. Circular means what? It means that these plane regions are circles, identical circles, and it is right. When we say right, it means that it is not tilted. It means that so these two circles are exactly on top of one another. So that is the meaning of being a right circular cylinder. So the one that you usually have in your mind as the cylinder, in mathematics we call it a right circular cylinder. But a cube or a rectangular cube, or these shapes that you are already familiar, are actually special cases of cylinder. And for this cylinder, we take this as an axiom that the volume is the area of that region multiplied by the distance between these two parallel planes. But if I go back to this picture, just to test your understanding, do you think that this one is a cylinder? Of course, you know that in this case, it doesn't matter. Sometimes, usually people call this one, which is on the floor, the base, but that's also a base. And if I do it the other way around, that's a solid object. So if I do it the other way around, it's still, these are the bases. Okay, but if I go back here, do you think that this shape that you see here is indeed a cylinder? No, why not?
It's not the same size.
Yeah, because even though this seems the same shape as this base, yes, but they are not congruent, they are not identical shapes. Okay, so this is not a cylinder. So this means that if I want to find the volume of this shape, I am not allowed to use that formula, V equals to AH. So what we do in calculus, we actually look at a very thin slice, as you see in the red picture here, and then this is not still a cylinder. I hope you agree. Why is that? Because this side, yes, is still different from that side. So the difference becomes less. Okay, so it is not that as the difference between this small one and that big one. It's still they differ a little bit, but the point is that this is a very close approximation to a generalized cylinder. And if I make this thickness infinitesimally small, the errors that I am making in approximating the volume of this slice with the volume of a cylinder is negligible. And that becomes a Riemann sum of a continuous function. When I want to add them up, it becomes the integral, if the function is well behaved and continuous, for example. Is that understandable? So that is the way we do it usually in mathematics. So for example, can you help me to do that? I want to concentrate on finding the volume of that slice, which we call it dV. It means an infinitesimal element of the volume that I am interested in. This is the volume of that red thin slice there. That one you approximated with a real cylinder. If I ask you what is the volume of this, what do you say? According to this formula, it becomes the area of that cross section multiplied by the height. Can you tell me first what the height is? You see, let me show it in the picture here. So what is the height? Do you agree? The height is the thickness of this red part. And this thickness is aligned in this picture along the x-axis. So this is an infinitesimal change in the direction of x. An infinitesimal change in the direction of x is denoted by dx. So that is the thickness which will play the role of the height of this sliced, very thin cylinder. But what is the area? The area is not fixed. So if I am here, the area is the area of this region. If I am getting closer to this far end, the areas are getting smaller and smaller. And if I go to the left end, the areas are getting bigger and bigger. So it is clear that this area of this thin slice depends on x, the value of x, where x is. Is that understandable? So this means that the area of that part is not something fixed. It is an area, but that area depends on x. Yes? And then I multiply it by the height. What was playing the role of the height is dx. So if I ask you what I have written on the word, you will tell me this is the formula for the area of that thin slice. Is it 100% equality? I mean, this is approximately the case. But when we write differentials or infinitesimals, we put inequality. Okay, and then I want to add up these volumes. How many of these thin slices we have? Infinitely many. If we have finitely many, we add them using sigma. Yes? But if we have infinitely many of them, we still want to add them. We still add them, but not using a sigma. We add them using an integral. So this means that the volume I am looking for is the integral of this expression ax dx. Okay. So of course here you see that it is from a to b, because I have mentioned that this point on x-axis. This point on x-axis is a. This is the smallest a for this volume. This is the smallest x, and this is the largest x. So I have to add them up between a and b. So this is your volume. Yes. This is a very important technique. I mean, especially if you're engineers, and for example, if you want to solve physics problems, this way of understanding the how. So integral is still a sum, but sigma is a sum over discrete values. Integral is a sum over continuous values. Yes. So this is the formula. Hopefully, I could able to somehow justify this formula. But of course, I am taking the volume of a cylinder as an axiom. This we are not proving. Okay. Any questions? For example, the first example I have written, determine the volume of a sphere of radius r. Okay, this is the first example we want to do. So we can do this problem in different ways, but let us do it in this way first, by slicing. So be careful, this formula of slicing is useful when you have your solid object and you want to find its volume. But you have to put up the coordinate system in a way that helps you, okay? In principle, you're allowed to put coordinate system anywhere you like, but if you put it in a very strange way, then of course you are making life harder for yourself. So tell me, if I have a sphere of radius r, and I want to set up my coordinate system, how do you set it up usually? For example, where do you put the origin of the coordinate system intuitively?
Center.
Center of the sphere, okay? So let us do that. So, for example, let us say that this is my sphere. This is very hard to draw these pictures, okay? I don't know if I have to. Let me just draw, and if something is not needed, I take it off. And it doesn't matter, I want to align it with that graph. So let me take this, the x-axis. Okay. And then, of course, if you want, you can draw another axis. You see that I haven't even emphasized the other axes. But for example, let me take this usually as y-axis. And the one that is coming out from the board is another axis, which probably we don't need that. That is the z-axis. Usually people draw it like this. Okay? But now the point is, I want to start slicing my sphere to thin slices, okay? And I want to use this formula, so I want to slice it perpendicular to the x-axis. What does it mean? It means, for example, I go a little bit forward, I am on the x-axis, this I will call it x, okay? And then I will slice my sphere perpendicular to this axis exactly from the end of this point. I don't know if I can draw it, but so something like that. Yeah, I hope that you can imagine it. Yes, so I don't know, this is the center. Yeah. It's a very bad picture, I agree, but hopefully you can imagine it yourself, okay? And then a little bit of thickness. My advice is that you just don't need to bring that thickness to make life harder for yourself, but imagine that slice has a very, very narrow thickness. That thickness is along the x-axis, so I am allowed to call it dx, yes? But if I want to use this formula, I need something else. I need to know the area of this green cross-section. So if you want, I can hatch it a little bit here. So I want to have this area of this green section, which hopefully you agree is a circle. But I want to do it as a function of x. I want to write the area of this green slice, green cross-section, as a function of x. So hopefully by symmetry you realize that this shape is a circle. So it means that I want to find the area of the circle. In order to find the area of the circle, I need the radius of my circle. Okay, so what is the radius of my circle? So if you don't mind, let me call this one R. This is fine. Okay, so this is the radius of my circle. And let us say that this is the radius of the sphere. I showed it in the example by little r. But the point is that this r is given to me and is fixed, because that's the radius of my sphere, but the radius of this cross-section depends on where I have this cross-section. Yes? I have to write this r in terms of x, but then it is extremely simple, you see that, yes? Because I want to find r, is nothing except, so r squared is what? Is r squared minus x squared. So that is this radius squared. And I want to find the area of this circle. What is that? It is pi capital R squared. But R squared is nothing except this one. Yes? Is that clear?
Why is it r squared minus x squared?
This is Pythagoras theorem. Yes? The hypotenuse squared minus this length squared gives me this length. Any questions? Yes or no? Because you don't seem happy. Understandable or not? Yes? Okay, so if it is yes, say yes. Is it yes or no? Yes.
So what is the point of doing it again? Doing r squared minus x squared?
No, because I am using this formula. For using this formula, I have to start slicing my volume. So I have decided to slice my volume perpendicular to the x-axis. So imagine you have a sphere and you cut it at some point perpendicular to this axis. In that case, if you open it up and look at here, you will see a circle. So I want to know the area of that circle because I need it in my formula. Okay? So in order to find the area of that circle, I need its radius. The radius of that circle is not given to me in the problem. The radius of the full sphere was given to me to be little r. But that is my duty to find the capital R myself. Then of course I make this triangle and then I realize this relation holds between these three quantities. And if you ask me what is the radius of my cross section, I will show you the radius squared of the cross section is little r squared minus x squared. And if I ask you, okay, what is the area of that circle? You would say that I multiply pi by the radius of the circle squared. The radius of the circle squared is this one, I multiply it here. But I have to add it up. X changes from where to where? The lowest possible x in this way of cutting is what? Minus little r. Because this is little r, so this is the minus r, and I go up to r. So it goes from minus r to r. And this is my volume. Yes? Yeah.
Since the sphere is even, could you technically say that the
Yes,
volume is 2 times 0 to r?
Yes, exactly. Or you can see that this function is even, and you can use the same trick. Yeah, you are always allowed to do these things, okay? So for me, it was what you said, you go from 0 to r, you get the volume of half a sphere, and of course you multiply it by 2. Or you can see from here, you remember when I go from a minus number to the positive of that number, and if my function is even, I can actually write it from 0 to r and then multiply it by 2. That's the same story. But this is an analytic way to understand it. That what you said is geometrical way of understanding the same thing. So anyway, I will actually follow you. So I will write it as 2, and then pi is a constant. I pull it out. Integral from 0 to r squared minus x squared dx. And I calculate this. I need to find a primitive function for my function. So I copy and paste 2 pi here. And then what is the primitive function for r squared?
R squared x.
R squared x. Hopefully you are not confused because r is not the variable. R is a fixed number. So it becomes r squared x, and this one becomes x cubed divided by 3, and then I run it from 0 to r. Okay, when I run it from 0 to r, it means that I replace all x's with r, and then I replace all x's with 0. For x 0, everything vanishes, so I just need to put it for r. So this becomes equal to 2 pi. Instead of this x, I put r, so it becomes r cubed minus r cubed divided by 3. And if I simplify it, so it becomes 2/3 of r cubed. And then this is the familiar formula for the volume of the sphere. 4/3 pi r cubed. Yes? Any questions? Understandable? Okay, so let us go to the next question. I have done it with GeoGebra and Gemini to draw this picture. Because I just wanted, because in the book, this is written only in words without any pictures. So I just wanted to, I was curious how the solid object looks like. A solid has a circular base of radius 3, all cross sections of the solid perpendicular to a particular diameter of the base are squares. It was not easy, but this is now, hopefully you can imagine this is your solid object, yes? So that do you see this cross section? This cross section is a square. So this solid object is the object whose base is a circle of radius 3, but it is designed in a nice way that when you cut it perpendicular to a particular diameter of the circle, and then you look it up, you see that you get a square. I was able to program GeoGebra to do this precisely, and then I used Gemini to actually make it a little bit more artistic. But hopefully you understand this is the object. But as I told you, in the problem in the book, you don't have any shapes. You just read the words you are supposed to imagine and understand it yourself. We want to find the volume of this object. Okay, so how should we do that? It's a little bit hard to draw, but let me only, so you have the picture in front of you, but I want to concentrate only on the base. Okay, so this is the y-axis, yes, and that's the x-axis, so that is good. So I am just looking at the base, and this is the x-axis. So here I have a circle of radius 3. So I have a circle of radius 3, so it is 3 here, minus 3 there, minus 3 here, and 3 there. And then what should I do? You know that that part of the shape is here, which you don't see. You can see it in that picture, but if you want to imagine it, it is somewhere here. Yes? And now what I do, I will cut my solid object perpendicular to this diameter. If you cut it, what do you see here? You will see just one line. And according to the problem, this is a square. It means that if you want to imagine it, it goes out, comes down, and goes back again. Can you imagine what I'm saying? So this is just that line there. So it is, for example, this line that you see here. Yes? So that's that line. And then the cross section, the real cross section comes out from the whiteboard, but in the form of a square. And what I need to do, it seems complicated, but if you understand what you're doing, it's extremely simple problem. Okay? So what I have to do, again, I will call it x. From here to here, this can change. This thickness, I call it dx. And I ask you what is the infinitesimal volume of that cross section is dx multiplied by area of that particular cross section. Okay, so the only thing I have to do is to find the area of the cross section as a function of this x. So, but you know that what is this cross section? The cross section, according to the problem, is supposed to be a square. So if I want to find the area of this cross section, what I need to know this length and multiply it by itself. Understandable? So that's because according to the problem, this cross section is supposed to be a square. Okay, so the only thing I need to do is to calculate this length based on x, in terms of x. Whatever I get is the length of my square. I want to find its area, so I raise it to power 2. Okay, can you help me to find this length from here to here based on x?
9 minus x squared.
Yeah, exactly. You see, that's the same trick. So for example, you can go here. If I ask you what is this length, this is the radius of my circle, which is 3. This is x. I am looking for this length. Let me call it L. So then L squared is equal to what? 9 minus x squared. Yes? But L is a square root of 9 minus x squared. Yes? I don't put plus minus because L is the length. But be careful, I want the total length. What is the total length? 2L becomes 2 square root of 9 minus x squared. So that is the total length. But now if I go back and answer this question mark is easy because it is 2L to power 2. And 2L to power 2 is easy because it becomes 4 and I remove the square root sign again. So it is a very simple calculation. You have to have a little bit of imagination. So dv becomes equal ax is this number, and then dx. What I need to do is just to integrate. Integrate from where to where? Minus 3 is the lowest x value, the highest x value is 3. So it goes from minus 3 to 3, and then I have 9 minus x squared dx. And this integral is so simple, just leave it for you to calculate. You can again use the same trick. You can go from 0 to 3 and multiply it by 2 because this function is still even. Okay, any questions? Okay. The next method that you need to know is the method of solid of revolution. Solid of revolution, you don't have your solid in front of you. For example, you want to find the volume of a sphere. Now, let me mention what the problem is. The problem is like this. For example, you have a function. For the time being, let us assume that this is above the x-axis. And then you have it from A to B. And this region has some area A in it. Let me concentrate on, because area is not important here, let me call the region R. That's a region enclosed by the graph of my continuous function and the x-axis and two vertical lines from A to B. Now you have to have some imagination. The problem is that I want to rotate this region about the x-axis, as if x-axis is the axis of rotation. It is not a solid object now, but if I do that, it will generate a solid object, a three-dimensional object. That object is called the solid of revolution. It is a solid object, but it is obtained after revolution of this region about x-axis, for example. I don't know how I can draw it, but hopefully you can see something like this will happen. Yes? So this will be a circular, something like this will happen. Yes, so can you feel it? So it will actually give you an object. There is, I mean, there is no name for that object, but that's an object, yes? So one question I want to ask you, is this object that we generate in this way, can I call it a cylinder?
No.
Why not? The bases are not the same, yes? But can I say that all cross sections are circles? Yes, all cross sections, if they are perpendicular to the axis of rotation, all of them are circles. Now, if I ask you find the volume of this guy, how do you do that? What do you do that? You will actually, again, slice your object into thin discs. That is called the disc method sometimes. So I give a little bit of thickness to this. Okay? And I concentrate on finding the volume of this small bit. If I want to draw it good, I mean, I don't know how I should put some dots here. So in principle, you don't see. This is the front one, this is the back one. Okay? So can you help me to find this volume of this disc? And then I have another disc, If I want to find the total volume, I add the volume of all these discs.
By f of x squared, so the function squared. And
okay, why is that? Because, for example, let me concentrate here. I take this x, okay? And then this thickness, because it is aligned with the x-axis, the thickness, I will call it dx. But in order to find the volume of this one, the general, I mean, this solid is not a cylinder, but this one is indeed a cylinder. It's indeed a real cylinder, okay? Somehow, if this is very thin. And then I will find the area of this circle and multiply it by the height, which in this case is this small thickness. Then this will give me the volume of this slice. And then I add them up using integral. Okay? So the thickness, which is the height, is dx. So let me write it. So this volume, the infinitesimal volume, is equal to the height, which is dx, multiplied by the area of this circle. But in order to find this area of this circle, I need to multiply pi by the radius of this circle. Okay, so let me call this radius. This is the radius of your circle. But I need this in terms of x. So can you tell me what is this height now? Yes, because I myself consider this to be x. And if I want to find this height, I feed this x into my function. It will give me the height, which is f of... No, here we don't need. I am assuming that this is above x. So this becomes f of x, but to the power of 2. Why power 2? Because the area of a circle is pi times the radius to power 2. So this length is just f of x, which is playing the role of the radius. I raise it to power 2, it becomes a square of the radius multiplied by pi. This is the area of this disk multiplied by dx. And then of course, if I want to find the volume, so what the volume is the integral of this expression from the lowest value, in this case lowest value of x is a, the highest value of x in this solid is b. And usually people bring this pi out, so that's another formula that you want to use to find your volume. Yes?
The idea behind this formula is the exact same as the previous one.
Yes, the exact idea is the same. Yes.
It doesn't matter what...
You can actually use this. Instead of talking like that, you can use this and find that formula. Because the only thing I need to do is to replace ax with pi f of x squared.
What is the requirement on the middle part's shape in order to use integral to calculate the volume?
No, the function, I'm assuming that this function is continuous and always above the x-axis for the time being.
So for that one and the previous ones, they are different shapes.
No, the philosophy is different. Here I didn't have my solid object from the beginning. Here I had the sphere in its full entirety from the beginning, and I want to find a method to find the volume of that object. Here I do not have this object in the beginning, I just have a region. And I rotate that region and then make an object, and then I want to find the volume of that object after being rotated. For example, if I want to use this method to solve the first problem, finding the volume of the sphere, I want you to understand that this is not exactly identical to this problem, but we can still use this one to find the volume of the sphere as well. What should I do? Yes?
Is it like you're thinking about that sort of top half of the sphere is like your
No, it's still, no, you don't have any solid object yet. If you want to use this method for finding the volume of a solid object, you first need to imagine a region so that after being rotated will generate the object you are supposed to find its volume. Yes? This is different. Here I give you the sphere, you find the volume. Here the sphere is not given to you. You need to imagine a shape, a curve. A curve is a one-dimensional object. It's not even 3D.
So I'm trying to say it's a line, like the top of a sphere. If you think of it, you think
Ah,
of
you
a line
said the
that you
top
then
of this-
rotate. It's like it's a semicircular
Yes.
line.
So
that you rotate in
so
two
sorry.
dimensions.
So I thought that you said
I
hemisphere.
was like, instead of thinking of a
Yes.
sphere.
Okay. What is that? That curve is what?
Root s squared minus x squared.
Okay. So you see, you have a lot of freedom. For example, if you choose your curve here, this will also generate a sphere for you. But you will make life harder because you are actually doing something asymmetrical. It's not very symmetric. Okay, so it will work, but it will make life harder. But if you want to be optimal, what do you think we will do? I will take my sphere with radius r. I ask myself, what function? So don't say the full circle. Of course, if I rotate the full circle, it also seems that I am generating the sphere. But that's not a function. I need a function. So tell me a function so that after being rotated generates my sphere. And that is very simple. The semicircle from minus r to r, and this is also r. Do you agree that if I rotate this region about the x-axis, I will generate a sphere with radius r? So I can say that the sphere of radius r is the solid of revolution after this is rotated. Okay, so then I can use this formula, but can you tell me how? So this becomes v will be pi integral f of x squared. So do you remember what is the formula for the semicircle? What is the function? Y is equal to square root of r squared minus x squared. This is the formula for the semicircle. Yes? So this is my y or my f of x. So in this formula, sometimes people write it as ab y squared dx. If they want to make it shorter to remember. So I have to write y squared. Be careful, don't write y squared. So it becomes r squared minus x squared dx, and it goes from minus r to r. And if you calculate this one, of course you will get the same answer. Yes? Okay. Okay, there is something that might be a good idea. What happens if I have this? If I want to use this technique, but I have two functions involved. Let me also explain this, because when I was teaching this in high school, people get confused sometimes. So let us say that I have a function f here, and I have another function g here, and I concentrate on this region between these two graphs and from A to B. Now what I want to do, I want to keep the distances the same. I want to rotate this region about the x-axis. It will also generate some solid object for me with some part of it carved out, which is hollow. But if I want to know the volume of that one, what do you suggest? Yes?
Just f minus g.
No.
So I mean, like you first rotate f, and then you rotate g, and then you subtract them.
Yes, this is correct. But f minus g, what you said is not correct. Yes?
Squared minus g squared.
So this is, if you think like this, is wrong. Okay? Because in high school many students wrote like this, and that is wrong. The correct one, as you said, is I will find the volume of the bigger one, which is what? Pi integral from a to b f of x to power 2 dx. And then I will calculate this volume of g after being rotated, which is supposed to be carved out from my object, so I will subtract them. So it will become pi g of x to power 2 d of x, and subtract them. And this subtraction is not that formula. Why? Because I can factor a pi out, and if I want to compose two integrals into one integral, I have to write f of x to power 2 minus g of x to power 2, and then dx from a to b. So this is the correct formula. So the power of 2 should not appear on the total expression, it should appear individually, and they are different. They are not the same. So be careful about this point, that's the only thing. If you want, we can solve this exam question. That exam question is also simple. So the curve y equals to the square root of 1 plus absolute value of x cubed, together with the lines x equals to minus 3 and x equals to 3 and y equals to 0, determine a bounded region in the plane. Determine the volume of the solid generated by rotating the region about the x-axis. That's exactly this problem. It was 2018, okay? So here a function is given to you. Y equals to the second root of 1 plus absolute value of x to power 3. It's always good to have some idea about the graph of the function, but don't be too precise, because probably they will not give you. Do you have any idea how the graph of this looks like? Don't be very pedantic, so just want to get an idea. So for example, if I go x is extremely large, then what happens to this expression? It becomes extremely large. And then if I make x negatively large, because of the absolute value, again y becomes positively large. And by the way, because if I change x to minus x, this function does not change, so it is even. So I can draw it on the right hand side and do the mirror image with respect to the y-axis. So what I'm trying to say is that this function is not a very strange function. So for example, if you differentiate this function, if x is positive, what happens? If x is positive, so the derivative of this one is 3x squared divided by 2 square root of 1x cubed. And you see that this function is strictly increasing. And if I put x equals to 0, the slope is 0. So it is not it's a very similar to parabola, but of course it is not parabola. So the graph of this function is something like this. I don't know. It should be a little bit flatter here, because the 0 is second order 0. Okay? And so it's just like this. Okay? And then this graph, and then which axis they have talked about? Y equals to 0 axis is just the x-axis. And the lines x equals to minus 3 to 3. So this region, according to the problem, is supposed to be rotated about the x-axis. You want to find the volume of that object. Here in this problem, you really didn't even need to draw the picture, because if you just put it in the formula, it could work, yes? So what is the answer? So I use the formula up there. So the volume that we are looking for is pi integral my function squared. You see, f of x squared. So when I square it, it becomes just 1 plus absolute value of x cubed dx. But I have to go for x. X starts from minus 3 according to the problem up to 3. So I have to write it from minus 3 to 3. And I have to calculate this integral. How do you do that?
Split it at 0.
We can split it, but don't do that. Because is this function even or not? If I change x to minus x, nothing changes. So this function is even. And this is from a minus number to the positive of the number. I prefer to write it 2 times integral from 0 to 3. But the benefit of doing it in this way is that now I don't even need the absolute value because x is positive. So the next step, I just simply remove the absolute value and then calculate just this integral. So this becomes 2 pi, and this is x plus x to the power of 4 over 4. I run it from 0 to 3. So what is the number? So it is 2 pi. If I put 3, 81, and this is 12, 93 over 4. So it is 93 pi over 2 volume units. Yes? Yeah.
Do we have to write volume unit?
No, I don't think so, but doesn't hurt. Write it down, please. Because usually, technically, we have to write, because that's not a pure number. It's supposed to be the volume of something. Okay, but there is something, might be you haven't studied that in the high school. That is called method of cylindrical shells. Okay? And there is one exam question, I want to solve it and see that sometimes it is really important to know this method, because they can design a question in a way that in principle you can choose whatever you like to calculate, but one method will be harder than the other method. Okay? So don't say that I will not learn it because all the problems in principle can be done by this method. Okay? So the problem is called the method of cylindrical shells. So this is why I want to explain it here for you. So let me first see what happens. I have still my region. Okay, so I have my region here. So let me see if I'm recording or not. Yes, so this is my region R. I don't want to write R here so that you're not confused, but this is my region R. This is my function f of x, and this is A to B. What I want to do this time, I want to rotate it about the y-axis. Okay, I can still use that method to actually solve rotation about the y-axis, but another method which is called the cylindrical shell method is easier. But I want you to understand, what I will do, I will concentrate on one thin part, slice of this. Let me make it a little bit thicker, but this is thin enough. This thickness is an infinitesimal thickness on the x-axis, so I will call it dx. Okay, and then from here to here, this is my x, which will change from A to B. But now I want your imagination a little bit. My goal is to rotate the whole region about the y-axis. What I want to do, I want to slice it into these thin rectangles and rotate this thin rectangle around the y-axis. You can also help yourself from the picture. What do you think this thin rectangle generates after being rotated about the x-axis, y-axis? Do you agree it will generate a thin cylinder, which is called a shell? This is called the method of cylindrical shells. Can you see that here? So here is that slice. If I rotate this about the y-axis, do you agree with me, at least you can imagine, that this thin shell will be generated? And if I go to the next rectangle, another thin cylindrical shell will be generated. And if I do it for all these thin rectangles, I am generating thin cylindrical shells one after the other. And the whole point is that I want to add up the volume of all these cylindrical shells in order to get the volume that I want. Is the idea clear? Yes or no? Okay, but help me now. The picture is in front of you, of course. Can you tell me how should I find the volume of that thin shell? Yes?
Well, you could find the area of x and x plus dx, I mean these circles from these radiuses, and then we could multiply it by the functions, right?
Yes.
And we can subtract the two cylinders from one another.
Yes, this is a very good way, but in this calculation you need to know something. If an infinitesimal quantity comes into calculation, any second power and higher powers of an infinitesimal should be put to 0. Okay? Another way of defining infinitesimal is a quantity which itself is not 0, but any higher power of the infinitesimal can be considered to be 0. If I want to follow you, so what you are saying is that, hopefully you agree that if this is not very thin, it's a little bit, is a finite value. Do you agree that I will get a scenario like this? Yes? So exactly identical. Yeah, something like that. This is called a cylindrical shell. It has two radii. One inner radius, so let me call it little r, and one the outside radius, the bigger radius, I will call it capital R. Exactly as you said, if I want to find the volume of this cylindrical shell, forget about this problem momentarily. How do you calculate that? You find the volume of the bigger cylinder, you find the volume of the smaller cylinder, and subtract them. What is left for me is the volume of this cylindrical shell. Is that right? Yes or no? Okay. Now can you tell me what is the volume of the bigger cylinder? It is the area of the base, which is pi r squared, multiplied by the height, so let me call the height h. So it becomes this. This is the volume of the outside shell, outside cylinder, outer cylinder, okay? And what is the volume of the inner one? It is pi, but the radius is little r squared, and then multiplied by the same height, because the heights are the same, and then subtracted. That's exactly what you said. If I factor a pi out and a factor h out, what is left for me is r squared minus r squared. So if I want to find the volume of a cylindrical shell, I need to know the height of the shell, and I need to know the radii of each one of them, the inner one and the outer one. So the outer one squared minus the inner ones. So if this is a very good method that you mentioned, do you agree that if I do this one, if I rotate that one, it will also generate a what? A cylindrical shell. Do you agree? But can you tell me what will be the radii in this case? The inner radius will be generated by this inner line when it is rotated. And what is that radius? Is from here to here, is x. So this means that the volume dV that I am looking for is pi, but instead of capital R, no, let me write a small r first. A small r is x squared. A small r is x, r squared is x squared. Yes? And then, can you tell me what is capital R? Capital R will be the radius of this one. So let me exaggerate a little bit. So let me make it a little bit thicker that you can imagine. So if this one is rotated, the radius of the inner cylinder is x. But if this one is rotated, the radius is x a little bit more. How much more? Dx more. So then it means that I should write it here, x plus dx to power 2. Yes? And then what should I do? I have to multiply it by the height. The height is this much. What is that? If this is x, if I want to know this height, I feed it into my function, it becomes f of x. So this is f of x. Yes? But what I said to you is this. So you raise it to power 2, it becomes the first one to power 2. 2 times the first one times the second one. Plus the second one to power 2, that is exactly what I just mentioned to you. An infinitesimal is a quantity which is not 0, but any higher power of that quantity can be ignored. And then it is minus x squared, and then I have f of x. So this x squared here and that x squared are finite, but they are gone. This d of x is infinitesimal of power 1, I have to keep it. But this one is second order, I just remove it. This can be understandable after we talked about Taylor expansion. But I just wanted you understand that. So then what happens? It becomes 2x times pi. So it becomes 2 pi x fx dx. So this is this volume of that thin cylinder. And then you want to add them up. Add them up means integration. So v becomes integral a to b 2 pi x fx dx. Yes, and then what happens? So it becomes 2 pi integral from a to b x f of x dx. And that's the formula that I have written it here. By the way, so for example, I can rotate about the x-axis, then the role of x and y will change. So for example, in some books, for simplicity of remembering, people write 2 pi, and then instead of x we just write x, but instead of f of x we put y. But we know that y is a function of x from a to b. If I rotate about the other axis, the role of x and y will be interchanged. That's easier to see this. Okay, but there is a good problem exam. I want to give you a little bit of break, and we solve this and we go to the second part of today's lecture.